Hi everyone. So in this joint work with Aurélien and Wouter, we revisit the use of Bandit tools for the purpose of adaptive planning in Minimax trees. Therefore, we present a new Bandit framework for games. So our motivation was to get a better theoretical understanding of Monte-Carlo Tree Search, or MCTS, which has been a powerful approach to build artificial intelligence for games. So the purpose of MCTS is to find the best action for a given player, call him player A, in a given state of a game, which is represented by the root of the Minimax tree. The white node represents state of the game in which player A should choose an action, and the gray node represents state of the games in which player B should choose an action. And of course, the edges are the actions that lead from one state to the other. So MCTS approach works, iterate the following steps. So there is a selection step in which a path from the root to a leaf is chosen. That is a sequence of action for player A and player B. Then the leaf may or may not be expanded, but the key point is that from this leaf we start a simulation, also called a rollout. That is, we end the game with a heuristic policy, and we see whether player A won, we get 1, or whether player A lost, we get 0. So tuning in practice the rollout policy may be tricky, but we won't worry about that in this talk, because we will consider an idealized model in which, in particular, rollout starting from a leaf will be unbiased estimate of the probability that player A wins starting from these states. And moreover, we will consider only a depth 2 complete tree, but in this idealized framework, we will be able to propose new algorithm with sample complexity guarantee that is bounds on the number of rollouts needed in order to identify the best action. So I'll go through the model we present first, and then I will present two types of algorithm, and if I have time, I will try to convey what optimality could be in this setting. So the model is simpler. It's simple. Consider a two-player, two-stage game in which player A chose one action I, then player B choose one action J, and we denote by mu ij the probability that player A wins after these two actions. So if player B is strategic, whenever player A chose an action I, player B is always going to choose the action J that minimizes the probability that A wins. Therefore, from the perspective of player A, what we want to determine is this Maximin action I star defined in the following way. And we are going to learn it based on well-chosen rollouts that will be assumed here to be a Bernoulli realization of the corresponding probability of winning. So basically, we are interacting with Bernoulli distributions, so sorry about that, but this might be yet another Bandit problem, where the arms are parameterized, actually this time by two parameters, so the two actions chosen by the player. But the main difference with the previous talks is that here we do not care about the arm with highest mean, but about the action that would be the minimax action in this setup. Still, the interaction procedure bears similarity with what has been shown before. At time t, we are going to choose a pair of action PTs, that is a path in our two-stage tree. Then we perform a rollout from the corresponding Bernoulli distribution. And we should, after some random time tau, stop the experiment when we are convinced that we have identified the Maximin action, and we make a guess A hat for this Maximin action. And our goal will be, for some risk parameter delta, that the value of the outputted action is within epsilon of the value of the best possible action, while using as few rollouts as possible. So this is very reminiscent of the fixed confidence best arm identification problems that we've seen this morning. And indeed, I will show how to adapt the main two approaches for the best arm identification problem to this Maximin action identification. So a successful heuristic for best arm identification is the use of lower and upper confidence bound. And I present here an algorithm, M-LUCB, that indeed relies on confidence interval on each means of the leaf at time t, made of a lower confidence band and an upper confidence band. So I illustrate here the algorithm in a particular case in which there are 3 actions for each player, and the corresponding arms are therefore grouped in bins corresponding to the action of player A. So the M-LUCB algorithm is a two-stage procedure that first pick one representative per action. That will be the arm in each group with smallest lower confidence band. So this will tend to align the lower confidence band in each group. And after that, hoping that most of the time the representative will be the smallest in the batch, we will perform a best time identification step on this representative. So here we do it with LUCB algorithm that make us sample at each round the leader, that is the representative corresponding to the actual Maximin action, so estimated from our current empirical mean, and a challenger that is one among the other representatives that has the highest upper confidence band. And we stop when the lower confidence band on the leader is within epsilon of the upper confidence band of the challenger. So here I show it on another run. So we perform a run on the algorithm, and here we note the number of times we have drawn each arm. So we see in particular that the lower confidence band of all arms in the Maximin action are larger than at least one upper confidence band per other arms. And we see that the algorithm mostly draws the smallest arm in each group, and very little, especially these arms. Okay, so what we prove for this algorithm is an asymptotic bound when delta goes to 0 on the expected sample complexity that scales like a complexity term h star multiplied by log 1 over delta. So I will illustrate this complexity term for you. So for each arm in the corresponding to the Maximin action, so here it's a particular setup of arms, we need to draw this arm in order enough to discriminate them from the arm mu to A, hence this inverse square gap. And for other arms, we need to draw them enough to either discriminate them from the smallest in their group, or so that the smallest in their group is discriminated from the Maximin arm. So this in particular is much better than what we could achieve with a naive adaptation of the best time identification tools. So the first idea would be, well, why don't we perform a worst time identification step in each batch, identifying the smallest, and then best time identification on the smallest arm. But in the case in which this arm would be very close to that one, we would have to pay the price to discriminate them that we don't pay necessarily with this more clever approach. So this was the simplest possible algorithm with Hoeffding-based confidence interval. We propose a lot of refinement, heuristic refinement of M-LUCB in the paper based on particular on information theoretic tools. And actually, we have provable guarantee for this type of improvement for another type of algorithm, which is the other type of algorithm used for best term identification. That is, it is made on elimination and uniform sampling. So the M-racing algorithm is equipped with a criterion to decide based on R sample of two arms P and Q whether mu P is larger than mu Q. So basically, this is a generalized likelihood ratio test. Refer to Aurelien's talk. It's a good idea in Bandits. And then M-racing is going to sample at each round all remaining arms and possibly discard some of them. But the main difference with classic best time identification is that here we are allowed to perform two types of elimination. Either we may eliminate an arm if we are convinced that it is much larger than another arm in the same group, or we may eliminate the worst action if we find another action for which all the arms are larger than this one. And so I don't give details, but we have improved sample complexity guarantee that scale with this information quantity. So I will just try to illustrate the algorithm I talked to you about on an example in which there are two actions per player. So I talked about the M-racing and the M-LUCB algorithm. So we see that M-racing is much better. But so the heuristic I mentioned for M-LUCB is first the use of KL confidence bound in the same algorithm. And actually, a much more efficient strategy that is still to understand is to use this type of Chernoff stopping rule that we saw in Aurelien's talk. And this is doing slightly better than our elimination algorithm. So I understood that I don't have to talk about the lower bound. But yeah, to conclude, we proposed the first algorithm relying on best time identification tools rather than UCB for Monte-Carlo Tree Search in a simpler setting. And of course, we need to go deeper. Thank you for your attention.